Hey everyone, on this lecture we are going to study the 01 knapsack problem, which is a very famous problem in computer science. This problem states, given as input a set of n items where each item I has a weight w sub I and the value v sub I, together with the maximum total weight that we can put inside the knapsack, we want to select a set of items to maximize the profit, that is, the value that we are going to put inside this knapsack without exceeding the total weight that we can have. Now, the 01 knapsack problem is differentiated with the fractional knapsack problem because in here, the items cannot be fractionalized. So either we take all of the item, okay, or we don't take anything of the item. Here we cannot fraction any item. So we already introduced and studied extensively the fractional knapsack problem, and we also saw the greedy solution to that problem. We're given an array of weights of the items and also the array of values. What we did is we selected those items that have the highest ratio, right? The ratio value weight. However, this approach does not work in this problem, in the 01 knapsack problem. Let's prove that this doesn't work. Suppose that we have this configuration, we have this example, we have 3 items only, so the value n is 3, and the total capacity, the total weight that we can put inside this knapsack is 50, right? So following the previous approach, we here calculate the ratio value weight of each item, right? So we basically divide V and we divide by the weight W for each item I. So for this first one, we divide 60, okay, divided by 10, this gives us 6. Here we divide 100 by 20, this gives us 5, and here 120 by 30, this gives us 4. So if we study now the ratios of all of the items, okay, following the previous approach, the algorithm will select the item 1 because it is the one that has the highest ratio, in this case the ratio 6. However, we can clearly see that this is not the optimal solution. This is not an optimal solution, as the items 2 and 3 form a better solution. If we take only the items 2 and 3, we will have a total weight occupation of 50, which is precisely what we have as a maximum, and the total value will be the sum of these two values, right? 100 plus 120, giving us a total value of 220. In fact, the optimal solution here is selecting the items 2 and 3. But as we can see, the previous approach that we did and we solved for the fractional knapsack problem does not here apply for the 01 knapsack problem. In fact, this problem in computer science is known to be NP-hard, since the 01 knapsack problem involves examining all possible subsets of items each time complexity grows exponentially with the number of items, and yet, while dynamic programming can be used to solve the problem efficiently in pseudo-polynomial time, this is polynomial in the input size and the capacity of the knapsack, the problem remains NP-hard due to its inherent exponential nature. So remember what is a NP-hard problem? We say that the problem is NP-hard if it is at least as hard as the hardest problems in NP, and thus every problem in the NP class can be reduced to it in polynomial time. The NP class refers to a class of decision problems in computational complexity theory, and these are the problems where given a potential solution, and there is a polynomial time algorithm that can determine whether the solution is correct or not. However, finding the solution itself may not be polynomial time solvable. And we see that this problem is NP-hard because every problem in the NP class can be reduced to our problem in polynomial time. And so now in this lecture we are going to prove that the 01 knapsack problem is NP-hard, and we are going to perform a reduction from the well-known NP-complete problem, the SAT problem, to the 01 knapsack problem. The SAT problem is a very famous problem that involves determining whether a given Boolean formula in the conjunctive normal form can be satisfied by assigning truth values to its variables. And the 0-1 knapsack problem, the one that we're working with, on the other hand, is about selecting items with certain weights and values to maximize the total value, okay, within a given capacity in the knapsack. Now, to perform this reduction, it is very important to remember the fundamental notion about reductions. And that is, if I have a problem A and I want to reduce this problem to another problem B, then we need to verify that whenever we have, okay, an element X that belongs to this problem A, it is a solution of this problem A, then this same element X, okay, after applying the reduction function that we give, also will belong to the problem B. And in the same way, if we have an element X that doesn't belong to the problem A, that is not a solution of the problem A, after applying the same reduction function, okay, this element will not be a solution of the problem B. What is important to bear in mind is this reduction function doesn't change whether the element belongs or not to the original problem. The reduction function is always the same. So here's a very simple reduction function that transforms an instance of the SAT problem into an equivalent instance of the 0-1 knapsack problem. First of all, given a Boolean formula in conjunctive normal form in CNF with n variables and m clauses, we create n items for the 0-1 knapsack problem, one item per variable. Remember, the CNF is a specific form used to represent logical formulas in propositional logic, and it is constructed using conjunctions and disjunctions or of literals, where a literal is either a variable or its negation. So the CNF is important, and it is an important representation because any logical formula can be transformed and converted into an equivalent formula in CNF, but we are going to discuss in other lectures this. So for now, just consider that we have this formula. This is a formula in CNF. How many variables we have? Well, we have here 1, 2, 3, and 4. We have 4 variables. So the value n is 4. How many clauses we have? Well, each conjunction separate clauses. So this is one clause, this is another clause. So we have 2 clauses. The value m is 2. So in this reduction function, what we do is, given this CNF formula, right, we are going to create n items for this 0-1 knapsack problem. So 4 items. Each item is going to correspond to a variable in the CNF formula. And what we're going to do is we are going to assign a weight of 1 to each item. And now, very important, for each clause that we have in the CNF formula, we are going to create an additional item for the 0-1 knapsack problem. And so we are going to assign a weight of m to each of these additional items. So essentially, since we have a value m equal to 2, we have 2 clauses, right? We are going to create now 2 more items. So we are going to have here 4 items, each of them with a weight of 1 in the 0-1 knapsack problem. And then we're going to have 2 extra items. Each of these 2 will have a weight of m. So each of this is going to have a weight of 2. We then set the capacity of the knapsack to m, and finally in this reduction function we set the values of all items to be 1. Remember, in the knapsack problem we have for each item its weight, but we also have its value, right? So here we set all of the items to have a value of 1. So all of the 7 items, or in this case all of the 6 items that we have here, will have a value of 1. Here we have their weights, and here we have their value. All of them have a value of 1. So now let's study the implications of this reduction function, and let's prove. Remember, we need to prove that if we have an instance of an element that is a solution for the SAT problem, then it will also be a solution of the 0-1 knapsack problem. And if we have an instance that is not satisfiable, it is not a solution of the SAT problem, it also won't be a solution of the 0-1 knapsack problem. So let's begin with the first case. So first of all, if there is a satisfying assignment for the original SAT problem, it means that there is an assignment of truth values to the variables that satisfies all the clauses in the CNF formula. Therefore, in the corresponding 01 knapsack instance, we can select the items that correspond to the true-valued variables. We only select those that are true-valued, along with any additional items that we have created for the clauses. Since the total weight of the selected items is at most the knapsack capacity, we can consider this as a valid solution for the 01 knapsack problem. Now let's suppose that we have a solution that basically it is an instance that doesn't belong to the class of problems, or to this problem A, which is the sad problem. Essentially we have an instance that is not a solution, okay, of the sad problem. So if we have an instance that is not a solution, doesn't belong to the set of solutions of the sad problem, this implies that there is no assignment of truth values possible to the variables that satisfies all the clauses in the CNF formula. Therefore, in the corresponding 01 knapsack instance, selecting the items that correspond to the true valid variables, along with any additional items that we have created for the clauses, this always will result in a total weight exceeding the knapsack capacity of M. Therefore, there is no valid solution to the 01 knapsack problem. Very well, and so with this we demonstrate the two cases of the reduction. If we have an instance that belongs, okay, this is a solution to the sad problem, it will also be a solution to the 01 knapsack problem, and if we have an instance that is not a solution of the sad problem, also it will not be a solution to the 01 knapsack problem. And so, since the sad problem is a well-known NP-complete problem, and we have made this reduction, then the 01 knapsack problem is proven to be NP-hard, because we have reduced an NP-complete problem, such as the sad problem, to the 01 knapsack problem. Okay? Therefore, this reduction demonstrates the NP-hardness of the 01 knapsack problem.